All right. So today's topic is physical change. We started talking about a car and the effects of the car. It wasn't in the beginning when you first drove it off the lot, it was brand new, no damage. Look at it now. It's got dents, rust, broken windows, and all that stuff. It has physically changed over the years. But in science, some substances can undergo the same type of changes. Okay, so here we're talking about ice cubes melting. That happens all the time, especially here in the valley. It's so hot that, if you don't have a really good ice chest, that ice inside is going to melt, very, very rapidly. One thing you always have to remember about a physical change is that the composition does not change. When I say composition, I'm talking about the formulas, okay? H2O, if you have it in the ice form, well, in the solid form, it's, same formula. If it goes from a solid to a liquid to a gas, the formula has not changed. That is what we mean by composition. Melting is an example of a physical change. A physical change is a change to a sample of matter in which some properties of the material change, but not the identity of the matter. Okay. Some physical changes are reversible, some are irreversible. Okay. The example about reversible would be the ice cube, that liquid water being refrozen, and we could call that melting a reversible physical change. Another example of change of states that are reversible is vaporization, liquid to gas, freezing, liquid to solid, condensation, gas to a liquid. All of those are reversible, right? We can always reverse any of those changes of state. Okay, and I'm pretty sure you guys know what condensation and vaporization is. If you don't, let me know. Dissolving is also a reversible physical change. For example, if you have salt and you have a pitcher of water and you dump some salt in there and you stir it, it will technically dissolve. You will not see it. Has it changed its formula? No. You can boil off the water and leave the salt behind. Okay? So just because you can't see it in water does not mean that it's still that it has completely changed and disappeared. No. That is not the case. So here you have an example of the Beaufort Sea. I don't know where that's at, but here they're showing the melting of the ice on top of the water. Maybe it's summer, and some of it has a tendency to melt, and then in the winter it reforms. Okay, that's what we can talk about that. Some examples of irreversible physical change is when you are helping with your dad and you have a big long board and he wants you to cut it into smaller pieces. Well, if you don't have an electrical saw, like, I don't know about you, but I didn't have an electrical saw when I was growing up. So anytime I went outside to cut some wood, I would have to use a regular saw. And you're sawing. And obviously you cut your wood up just like your dad has asked. But something that is irreversible is the fact that you cut that wood. The sawdust that falls also is a irreversible physical change. It's still wood, it's just in a different form, and you cannot go back to the original. There's no way you can pick up all the sawdust and pack it back so it looks exactly like the board it used to be. If you're outside cutting grass, there's no way for you to go and pick up pieces of grass and stick them back on the plant. Pulverizing is just breaking apart large rocks into smaller rocks. You can't put the rock back together. Same thing when you're cutting a mesquite tree for your carne asado on the weekend. Once you've cut up the tree, you can't put it back. Those are examples of physical changes that are irreversible. You cannot go back to the original form. Okay? We're not going to do that. That one's really, really, I don't know. I didn't like it. But I do like this. It's a simulation. It's really neat. I like it because it shows a lot of the molecules and what's actually happening. Which things that camp out are undergoing physical change and which are undergoing chemical? You can escape a lot when camping, traffic, crowds, chores, but you can't escape science. And then they're going to give you some examples. First example, powering up a flashlight. Science.
That's chemical.
Sorry?
That's chemical because of the battery. Because, like, you know, like the battery has just chemicals
Right.
turned on.
Heating water for tea. Burning wood. Okay, so these are some of the ones we're gonna discuss, but we're gonna go into more detail. All of these processes involve changes in the properties of matter. Which of these changes are considered physical? Which are chemical? All right, let's see. Come on, hurry up. It's so slow. Okay, so here you go. We're going to be clicking on different ones and we're going to analyze what's happening chemically. Okay. So here you have water molecules in the liquid form turning into gas as it's being boiled. But if we look at the chemical equation at the bottom of the page, we notice that the formula of water has not changed. This would be an example of
Physical.
Definitely a physical change, right? We had a bunch of molecules, but as you start heating up and boiling, you start to vaporize them and they start to go, it starts to get lower and lower and lower because you're losing water molecules, okay? That's one. This one. There's two versions. So here you have your wood molecules.
Now that one is physical because you're gonna cut wood. That's it. You're just gonna cut wood. That's when you're cutting wood. That means it's changing shape. That's what it is.
Right. Reversible or irreversible, though, Gael. So here you have your formula for the actual wood. As you can tell, you got 6, 10, and 5 carbons, hydrogens, and oxygens. Same thing after we've chopped that wood up. But if we look at wood and we begin to burn it, well, all those molecules floating around is oxygen. Okay, and then you have the same molecule at the bottom. And look at what happens when you get, all right. So once that fire starts to burn, it separates all the atoms and they reconfigure to carbon dioxide and water. Okay.
Well, that means ashes, right?
Right. Carbon dioxide and water. Well, actually, ashes is what's left over after the carbon dioxide and the water has dissipated. Okay, because both of those are gas form and everything else that didn't get used up turns to ash. Okay. Let's go back. Let's look at the flashlight. And I want to show you this one because glass breaking, I think, is too easy for you guys. So here you have your battery. You hit the switch. It connects the circuit and you have a transfer of electrons, right? You have your purple elements losing electrons while the orange will be gaining those electrons, right? Until finally you have used up all the electrons that are provided in this battery. Okay.
And that's chemical property.
Definitely, for sure. What about this one? Somebody said it's cheese, miss. Click on the cheese. And I was like, no, it's butter. So you can see your polysaccharides inside the butter and it gets cut in this case.
And that makes physical changes.
Definitely. And if you look at the formulas, they're exactly the same on both sides of my equation. 57, 104, and 6. 57, 104, 6. 38, 57, 99. 38, 57, 99, and then we have our water. Okay, another example of physical change, but let's look here at melting butter. This one takes forever. So you see your polysaccharides in there floating around, waiting to go into your body. You know, most of the time those guys are, you have too much, it's bad. So, so we have changed from a solid form to a liquid form. But what else is happening? What do you notice is also
it's evaporating also.
Right. There is vaporization. Okay. What molecule is doing that? Well, we can look at the equation and we see, okay, yes, this guy's a solid, he's a liquid. And now both of them have become liquid, but look at what happened to our water. Our water has now vaporized into a gas. All of these are examples of physical change because nothing is changing as far as the formula is concerned. What about this one? This will be the last one we cover. So we fill it with some water. You notice it's obviously going to go through the filter. All the yucky stuff will stay in the filter while everything else, all the good water, is now free. Yeah, you got a couple of ions in there, but nothing that's really going to hurt you. All right, so this is more of a physical change, right? Because you're not changing the water chemically, you're just basically filtering all the bad stuff out.
Like the germs and everything.
Exactly. Oh yeah. So, all right. Is there any questions about the simulation? What do I do if I do this? Oh, okay. No. All right. That's it. Okay, so in summary of this section, physical change is a change to a sample of matter in which some properties of the material change, but the identity of the matter does not. A physical change can be reversible, where the original form of the matter can be restored, or irreversible, where the original form cannot be restored. Melting ice, grinding wood into sawdust are all examples of physical change. So you got 3 review questions to do. Define physical change. Why is melting an ice cube a reversible physical change? And then give an example of an irreversible change. We're going to go ahead and go to our other section. I hate my neighbors. They're always jamming out. Okay, so here you have 2.1 matter, mass, and volume. If you notice, this is a picture from a scanning tunneling microscope. It's an extremely powerful and I'm pretty sure expensive microscope that shows cesium here attached to a gallium arsenide molecule. Okay. This is just a reminder of, what is actually being seen or what it looks like at the molecular level when, just looking at regular compounds. I was telling my students earlier that it kind of looks like one of those things that you roll onto your bed, like to make it a little bit more softer and like more supportive of your back. But I had a student last period, or I think 4th period, who was like, "Miss, it looks like one of those cartons for the eggs." And I was like, "Oh yeah, it does." And everybody's like, "Yeah, that's a good one." I was like, "I had never thought of that one." But for me, it looks like the lining for your bed, so it's for that extra support. But it also can be a carton. It could also be a carton of eggs, okay? So an empty carton of eggs. All right, so all of this should be reviewed. This is all old stuff from your old science. We've already talked about mass and volume when we talked about density. So we're going to go really, really quick on this, okay? So bear with me. And if you have any questions, well, just reach out, okay? Matter is all the stuff that exists in the universe. Everything you can see, touch, is made up of matter, including yourself. Things that aren't matter are items that you can't see. For example, the light as it transfers from the source to the ground. You can't really see it. You know it's there because it's bright in your room, but you can't really touch it. You can't really see it. Sound is the same way. You can hear me talking, but can you see the sound waves traveling to your ears? No. In science, matter is defined as anything that has mass and volume. Okay. Mass and volume measure different aspects of matter. Okay. For example, let's start talking about mass. Mass is a measure of the amount of matter in a substance or an object. Okay, so it counts everything that it's in there. The units for mass is the kilogram and the gram, right? If you're weighing something that's really really heavy, obviously you're going to be using kilograms, but if you're weighing something that's really really light, you'll be using the gram. Okay. And no, I'm not talking about Instagram. But anyways, here in our lab, what we use is a triple beam balance or electric balances. We don't have a lot of electric balances, so for the most part, we use triple beam balances. But be careful when we go back to school, guys. They're really, really old and they break so easily. All right. Here you have an even older type of balance, okay? And if I zoom in a little bit, you can see that this little knob right here has a point. That point is supposed to line up with the other point if they are of equal weight. If they are in this case, they're unequal because one weighs more than the other. Okay, in this case, we have 1 kilogram on the right and a bunch of fruit on the left. Okay, now what can we say if the fruit is higher than the weight that we put on? Well, we can say that the fruit is less than 1 kilogram. Okay, if it was even, you could say it's 1 kilogram exactly. And if it's the opposite, the weight's on top and the fruit's on bottom, then you could say that the basket of fruit is much heavier. Okay, more than that kilogram. Okay. Now, something that always gets mixed up is mass versus weight. Mass versus weight can easily be confused because it involves how much stuff weighs. But when it comes to mass, it's all about how much matter. When it comes to weight, you are taking into account your gravity. Okay, and gravity is all around the world, right? We know that gravity is 9.8 something grams per Newton. I don't know. I don't remember. I'm not physics. It's been a very long time since I taught physics. But you have to remember that since we have gravity, every time you jump, gravity holds you down. Okay, gravity holds everything in my room down. If not, you would see my drink floating in the air, phones floating in the air. We don't have that problem because of gravity. Okay, and thank God for that. Okay, I don't want to be floating around and be worried if I'm going to float away into space, right? So let's say, for example, they give you a question here. The Earth's gravity, an object has a mass of 1 kilogram, but has a weight of 2.2 pounds. How much does a 10 kilogram object weigh? Well, since you know that you have 10 kilograms, each of them weighs 2.2, a little bit of multiplication, and bam, you have your answer. 22 pounds is the weight for that 10 kilogram object. Volume is another important unit, variable, measurement that we need for a lot of the calculations that we're going to be doing. Volume itself is a measure of the amount of space that a substance or an object takes up. The basic unit for volume is known as the cubic meter, but smaller volumes may be measured in centimeters cubed, right? When we're talking about density, everything was in milliliters per centimeter or grams per cubic centimeters or grams per milliliter. Okay, why? Because we're usually dealing with small numbers. Okay, the only one that was in meters per or grams per liter or cubic meters was gases, because gases are way different. Okay. um how the volume of matter is measured depends on its state. Okay, so there's different ways to measure matter. If it's in the liquid form, you'll probably be using a measuring cup or a graduated cylinder. If it's in the gas form, we know that gases have a lot of space in between the molecules. So, with enough pressure, we can force a gas into just about any space that we need it. And it'll take the volume of that container. Okay. So, if I have a tank and it has a 10-liter volume, I can only fit, 10 liters of gas. Okay. Um, if it's a solid, if it's a regularly shaped solid, for example, my post-its, right? My post-its have a regularly shaped. There's a length, there's a width, and there's a height. And if I multiply the three, I can easily calculate the volume of my post-its. Now, if you have a solid that doesn't have it doesn't have a regular shape, you're going to use what's known as the water displacement method. Okay. So I don't know if you've ever like filled up a tub and then like jumped in, and maybe you filled it up a little too high that the water goes over. That is what we call water displacement. Okay. And we use that in science to find the volume of objects that don't have a regularly shape, that don't have length, width, and height to measure. Okay. So let's talk about that. Here's some examples on how to calculate volume when you have length, width, and height. You just multiply, right? And you've learned that from past classes. I'm not going to really go into that. But water displacement is displayed here. Okay. Now, if you have a graduated cylinder and I don't know, Mr. Basan goes and puts a little bit of water, and Gael, when he gets back, he tries to read it. Well, he's going to start to read. He's going to say, okay, well, there's 1, 2, 3, 4. There's not 5. It's a little bit less. So it's like 4.2, 4.4, 4.6, and then 4.8. And then Gael puts it in his notes. Okay. Now, a little bit later, Basan dumps in our little dinosaur, and Julian reads that it has gone up. It has passed the 4.8 mark, and now we're at 5.2, 5.4, 5.6. Now, we need the difference between these two measurements to find the volume of the irregularly shaped object. In this case, dinosaur, a little dinosaur toy. Okay. And if you subtract those two, they give you the answer. It is 0.8 milliliters in volume. Okay. Now that you have the volume, now that you have the mass, you can calculate density. And density is one way to identify what type of substance, what type of compound that you have encountered or that you're using. Okay. Let's summarize what we learned today. Matter is all the stuff that exists in the universe. It must have mass and volume to be considered matter. If you don't know what mass is, mass measures the amount of matter in a substance or an object. Okay, and don't get that confused with weight. Weight takes into account gravity. The basic SI unit for mass is the kilogram. When it comes to volume measures the amount of space that a substance or an object takes up. When it comes to the units for volume, there's like so many, right? For mass, it's the kilogram and the gram. For volume, it could be cubic meter, it could be liter, it could be cubic centimeter, or it could be milliliter. 4 units right there for volume. Okay. Your review questions. How do scientists define matter? What is mass? What is the basic unit of mass? What does volume measure? Name 2 different units that might be used to measure volume. And explain how to use the displacement method to find the volume of an irregularly shaped object. Okay?